So I'm going to start the session today. Welcome to this summary session. Today I'll be talking about a few concepts that were discussed over the course of 12 weeks. Some important points that we should keep in mind, and it will be kind of like brushing up of concepts. And prior to that, I'll show some of the tests and how to conduct those analysis using R. Whatever theoretical things that we learned, uh, we'll see the software implementation of those things. Okay. Before so first things first, I'm going to go week wise, and then as and when I encounter the tests, I'm going to refer to the software version. Is it fine?
Okay, ma'am.
Okay.
Ma'am, one problem is there.
Yes.
Can I discuss?
Yeah, of course.
मैम जैसे कल आपने बताया था स्टेशनरी टेस्ट हमने किया था, तो ये स्टेशनरी टेस्ट तभी करेंगे कि जब डाटा हमारा स्टेशनरी होगा। नॉन स्टेशनरी के लिए तो ये कोई भी टेस्ट नहीं होगा ना, जैसे ACF हो गया, PF हो गया, डिकी फुलर टेस्ट।
Non-stationarity, if there's non-stationarity in the data, first we have to remove the non-stationary components. So that is where the decomposition will come into play. So we have to remove the seasonal and trend components, get the irregular part, and test for stationarity in that irregular part, because we know the presence of trend and cyclical and seasonal fluctuations, they are going to contribute to non-stationarity. It will not become stationary that way. So we should focus on the irregular part. Now if suppose that is also non-stationary, so then we have to go for the differencing of first order, differencing of second order, and then we should go and test the first order, second order, third order. Then we should go and test the augmented Dickey-Fuller test. If we find that, let's say in second order it is getting stationary, then we should fit an ARIMA P to Q model, where P and Q are the orders of the moving average and the um, autoregressive processes respectively, and those P's and Q's we will get from the ACF and PACF plots. Is the idea more or less clear? Because always it's not very clear how to which order of the P and Q we should be taking from real life PACF ACF graphs. So we should, I would say, be a little careful and see where strictly after which point most of the points lie within that 5% level of significance. So let's say after you difference of second order, first difference, second difference, the series is becoming stationary, and then you fit an ACF and PACF on that model. If you see that for ACF after lag 2, then it should be the moving or average order should be of 2, and if it is PACF lag 1, then it should be a ARIMA 211 model, something like this. Okay.
Ma'am, for the stationarity and the statical signifier, it is compulsory to satisfy that to run the ACF and PCF and dicky fuller test.
Those are tests to get unit roots. It's not, those are, see, ADF is the statistical test, and if it looks stationary, the main thing is that stationarity means what? Means that there is no variation and the expected mean of the series remains constant. So if you believe that that is the case, then you may not go for test, but that is like giving you more mathematical evidence about how correct you are regarding your assumptions and observations. So in any time series will have a stationary component and will have a non-stationary component, real life time series. So our goal is to remove the non-stationarity part, either by fitting trend line, removing trend, deseasonalizing, or like formal decomposition of decomposition does what? It is calculating the moving averages, that will be an estimate of the trend. It is calculating the seasonal indices, estimating seasonality, removing it from the variant and getting the irregular part. So instead of doing that decompose thing, we can also fit a trend line, deseasonalize, however we learned that, and then whatever residual series that we get, we should go and test for stationarity of that series. If we find it is stationary, then we can go for modeling.
Okay, ma'am.
Anything
Okay,
else?
ma'am. Ma'am, can you explain one more time that carillograph in a dotted line, then the bar? Yesterday you have drawn between the if our that bar is between the dotted line, and
Okay,
then
okay,
it
okay,
signify what?
okay,
Oh,
okay,
that one.
okay. So let's say this is my ACF or autocorrelogram function, and here I'm going to represent lags. Okay. Uh, let's say this is my ACF, and this is the lags. So this one, these lines, especially the first one at lag 0 will be 1. So this is actually the correlation between ET and ET minus I, where I is the ith lag. So these are the serial correlations. Okay, so that is why, if and that is going to determine the moving average process. So let's say this is the 5% level of significance, beyond which we consider, if I have something like this, we would say that the autocorrelation between the, let's say this is 7, so ET and ET minus 7 correlation is 0 if it falls within this boundary. Okay, so that is going to determine the moving average process that we are going to have, MAQ. So here if I say 1 2 3 4 5 6, beyond 3 we see everything is falling bill. So then if this is a moving average process, it would be a moving average process of lag 3. Is it clear? This is the autocorrelation function, or this is the, we actually we call it correlogram, and these are the errors. So this would, or something, so errors we are saying because of the irregular part. Let's say this is the irregular part. Okay, so correlation between these and this one will give us the I mean, this is the ACF, and this is how we should determine the order of the process. So if you have a, suppose we learnt about this PDQ, right? So this is, let's say, the original series. So then D order would be 0, P we would get from the PACF, and Q we would get from the ACF. So here it would be, if I say, if we have the partial this, let's say this is the PACF graph, which will determine the order of the autoregressive process. So let's say at lag 1 I have lag 2, beyond lag 3 everything is falling like this. Let's say only at lag 1 I have a spike. So then I would fit an ARIMA 103.
It's mean that if the spikes are between this dotted line, that is the 5%
Yeah, it
limit,
means we'll
then
consider that the correlation is between this order and the difference lag is 0.
0.
And here
Okay.
if it falls, then we'll say the partial correlation is 0. Okay,
Okay.
this
Okay.
is the
Thank
line
you.
of
Okay. Thank
significance.
you.
Okay, all right. So I'll start with what was discussed in week 1. So we discussed the stages of empirical research. We learned more about population sample. So these terms are very important. You can expect questions. Uh, Population sample, what is the difference? What do we mean by a representative sample and a random sample? What is the difference between theory and hypothesis? How to formulate hypothesis? And then we learnt about the types of variables. So it could be quantitative, uh, under quantitative it could be discrete, like taking values 1 2 3 4 and nothing in between, or it could be continuous, 2.5 3.7, can take any value in the real line. Or it could be qualitative, where there it could be a nominal variable where there is no inherent rank order, or it could be an ordinal variable where there is some rank order. Okay, so each data point we'll call it observation. We learnt about the data collection techniques, which is primary and secondary. When do we call a data as primary data and when we call it secondary data? So primary data is you are collecting data by yourself. Okay, so first hand, if I may say this word, then first hand data which is collected and analyzed and processed, that is the primary data. But secondary data is that data set which has already been processed and collected, we are just accessing it, so that would be secondary data. For example, every year if we go for census, then census is a primary data collection. Now if over the years I want to look at the census data and do some analysis, then I would be working on the secondary data. Okay, then we learnt about types of data, which could be cross-sectional, time series or panel. Panel data is combining the two, cross-sectional and time series. So cross-sectional is we are observing uh, let's say 500 individuals belonging to the same age, that would be a cross-sectional data. And time series data is we are observing like one individual over time. If we combine both of these, we would have panel data. So we learned about a very we had some discussions regarding the data analysis techniques. So we could fit descriptive statistics or it could be inferential. So descriptive statistics means fitting mean median model, getting the 5-point summary, looking at the box plot and the charts and everything, the frequency tables, that every other thing, tabulation, frequency distribution, those would be fall under descriptive statistic. And inferential is that we want to we have a population in mind. So let's say this is my population, so we have a representative sample uh, from the population. We are calculating the value of the test statistic, and we are uh, not exactly test statistic, we are getting the sampling estimate of the parameters and hoping that it satisfied some good criteria like unbiasedness, consistency, it is minimum variance. So that we can say that actually the population parameter, one possible value of that is whatever we obtain from the sample estimate. So we learned about the stages of econometric modeling. What we do, we usually want to find out a relationship between a predictor and a response. We set some mathematical formula which is suggested by the economic theory, and then we add some error stochastic term to it, and then try modeling it so that we get the relationship based on the data that we have in our hand. So that is what we do. We talked about predictors and responses in this context, and how we should set up hypothesis testing under certain model assumptions. Then we spoke about categorical data and how to get the tabulation, frequency table construction, how we can do it, how we can construct any contingency table, how we can construct group frequency tables. In this context, we learnt about class intervals and class width, class boundaries. So these are important terms which should be careful about. Then we learned how to draw frequency distribution graphs and also relative frequency distribution uh, would give a close approximation of probability distribution. This one we learned. Then we learnt about some measures of central tendency, which is a measure of central location, dispersion, which is a measure of spread, and skewness, which will show how if it is falling, if the data set is like this, like sorry, if the data set is something like this, or it is something like this, like inclined to one area, highest frequency in either of the ends, that would be skewness. We learned about measures of central tendency. This was the arithmetic mean, geometric mean, harmonic mean. They share a relationship between these three, so that is quite important. We learned about mean, median, mode, and what happens to uh, to their relationship in case of a positively skewed or a negatively skewed distribution. How can we, from their interrelationships, how can we identify skewness? These also we learned. Okay, I hope you remember this. So dispersion measures were variance, standard deviation, range, interquartile range, and skewness. Now one thing is to remember, if we have a box plot, let's say I have a box plot like this, so whatever outlier value these are beyond, let's say this is less than uh, the q1 minus 1.5 IQR, and this point will be beyond q3 plus 1.5 IQR. Okay, where this is the interquartile range. Then we learnt about effects of outliers, scaling, and shifting of observation on summary measures. So what we mean by that is, if we have if we have a random variable sec x, which is variance of x, let's say is 5, so variance of ax would be a square into variance of x, which is 5, but variance of x plus b would be variance of x. So this is dependent, variance metric is dependent on scale, but it is not dependent on shift in mean. Okay, it depends on scale but not on the shift. But if you have something like this, expectation of x plus b would be 5 plus b, and so this mean measure is dependent on both, an expectation of ax would be a of expectation of a, so it will be 5a. So mean will be affected by both scaling and shifting, but variance will only be affected by scaling and not shifting. Okay, just a recap. Then we moved on to probability distributions. So there were so many types of so first we learnt about random variable. Random variables could be of two type. It could be either a discrete or a continuous variable. So we learnt about the PMF, CDF, expectation variance, and median in the context of binomial and Poisson. We when we, as an example of continuous random variable, we learnt about exponential and normal. So now I'm going to show you how you can get these PMFs and CDFs, because obtaining PDF is a little difficult, like exact probability, but I can show you how you can obtain the CDF and PMF for a binomial distribution or a Poisson distribution. So let's say you want to generate random numbers. I'll stop my screen for a second, and please let me know if you can see the RStudio. You can see it, right?
Yes, ma'am.
Okay, so let's say you want to generate, so I want to generate 100 observations from a binomial 10.5. Okay, let's say this is my task. So the command is rbinom. So if I do an F1 over here, we'll see what it does. So this one will generate, so our binom is going to generate random numbers with this size and probability. So size will be, I want to generate 10 numbers, okay, and size is the n parameter. I want to generate 100, size of 10, and p equal to 0.5. So if I run it, I'm going to get 100 random numbers sampled from the binomial distribution. Now if I want to find out the probability that an x which is following binomial 10p is 7, this is the thing I want to find out. So then I have to write d binom. D binom is going to give me my PMF or mass function, okay. So this is similar to probably, this is PMF at x equal to 7, whatever I am showing. So if I write d binom x, I will put 7, size equal to 10, p equal to 0.5. So the probability is, this thing is 0.117, let's say. Is it okay? Now if I want to find out probability x less than equal to 7, so for that I have to write p binom 7, size equal to 10, probability equal to 0.5, and lower dot tail equal to true. Okay. And if I have to find out probability x greater than 8, then I have to write p binom 8, size equal to 10, lower dot tail equal to false. And prob equal to 0.5. If I have to write this p binom 10, then it will be 0. If I have to find this one, okay. Let's say, let's find out 9. So then this is equal to d binom 10, size equal to 10, p equal to 0.5. Is it clear?
Yeah.
Okay. So if these are to find out the points. Now if I have to find out, find probability x less than equal to x. Let's say I'm going to find out k. Find k such that probability x less than equal to k is 0.87. So then I have to use this quantile command. So q binom, here we can see how we should use it. So q binom, we have to give the probability 0.87, size equal to 10, top equal to 0.5 and lower dot tail equal to true. So which is that point below which 0.87 area lies? So this will be 7. Okay. Is it clear? So for each of the things we have similar. So for Poisson, if we have R poise for generation of random number, D poise is for getting the probability mass function, P poise is to get the cumulative density function, and Q poise is to get the quantiles. Similarly, for exponential we have REXP, DEXP, PEXP, QEXP, REXP. For chi-square, it's the same thing. It's D chi-square. Sorry. So this will give us D chi-square, P chi-square, Q chi-square, R chi-square. Okay. For T also, it's RT, students distribution. For F, it is capital F. Okay. Sorry. Sorry, small f. DF, PF, QF, RF. For norm also, it's same. R norm to generate random numbers. D norm would give me the probability. P norm and Q norm. Mostly we would use these three, P, Q and R. And in case of discrete things, we are going to use D things as well. Okay. So whatever and however these are getting calculated, these are my random variable and distributions. Can you see the PowerPoint screen? Hello?
Yes, ma'am.
Okay. Okay.
Visible.
Okay. Okay. So, okay. While this is done, we also learnt about binomial and Poisson approximation to normal, how we should do some sort of continuity correction. We learned some more on the standard normal. So we learnt about the critical points. So let's say if we have this one, then 1.96 above area is 0.025. If we have 1.64, then the above area is 0.05. So these are the critical points that we can obtain using the Q norm function, as I was saying yesterday. Okay. Also we learnt about how to use statistical tables and the other related distributions, which are the chi-square, T and P. Okay. Then in week 7 we learnt about the statistical inference methods. There are two primary methods of in estimation, which is the one is the point estimation and the other is the interval estimation. So we could have a moment measure of estimation, moment based estimation, or we could have maximum likelihood based estimation. And we also looked at interval estimations when we have a large sample cases, typically greater than 30, and when we would have small sample case less than where the sample size is less than 30. So in case of getting confidence intervals for means, we saw that if the sample size is less than 30, we would have something like this mu into T critical into sigma by root n something. plus minus. So this would be T critical for small sample case, and it would be Z critical for large sample cases. This is what we saw. Also, I was talking confidence level is this. Usually we have seen 95% confidence interval. So this will determine. So since it is always both sided, the point to keep in mind is that if I have 90% CI, my critical value should be, let's say T or Z, should be 0.095, sorry 0.05. But if I have 95% CI, it should be T 0.025. Okay, this is an important thing that we should keep in mind, because whatever confidence interval is stated, that is usually that is always both sided. Okay, so adding the two sides up, we should get 1 minus that thing, 0.95. Okay, so as I was saying about the desirable properties of an estimator, it is desirable that we have an unbiased estimator, we have a consistent estimator, that is as n tends to infinity, the variance of the estimator is going to 0, which essentially implies that whatever our estimate is, the sample estimate is moving closer and closer to the population estimate as we increase the number of samples in our study. Then we talked about relative efficiency, which is nothing but a ratio of the standard deviations. So we would want our variations to be very efficient and precise. So that is one thing. And then we also talked about minimum mean squared error. So uh, we also saw that the this is achieved for an OLS estimate under for an OLS estimate, the to get to the estimate, we use this principle that the mean squared error should be as low as possible. Also, we talked about the student's T distribution, how it is obtained, and about the T table. And as I was saying, we learned a few things on the estimation of mean variance and sample size determination also from this, because if we have the probability around this thing equal to something, or if we can, let's say, the 95% confidence interval, we have it something like this, 5 to 10. So we can equate this with 5 and 10, and if we know the values of mu and sigma, we can get n from by equating these two things. Okay. Also, we learnt about hypothesis testing, what is null, what is alternative, what do we mean by a level of significance. The important thing here is the type 1, type 2 and errors and power. So type 2 error and powers are related. 1 minus type 2 error is my power, and what it means and how the goal here is to maximize the power, keeping this thing at a constant level of significance. Okay, then we learnt about rejection rule based on p-value method and traditional method. So we could base our rejection rule based on some critical regions, like when we uh, let's say this is my observed f and it is greater than the f critical. So this is based on critical region that we devise, keeping our alternate hypothesis in mind. And this will also reject H naught. And also we reject H naught if p-value of the test is less than 0.05. So this method is based on p-value. Essentially they are the same thing, but we some tests would output this one directly. For some tests we can calculate this one. Okay, but usually from whatever the softwares throw as output, they would be based on, mostly they would be based on p-value. Okay, All right. So then we learnt about the Z test. So as I was saying, whenever we have a large sample case, we would approximate it with a Z test, like equality of means, equality of proportions, where population mean is equal to some specific value. So those, in a large sample scenario we would use a Z test, and in a small sample scenario we would use the student's t test. Also, if we have before after situations on the same individuals, then we can use paired t tests. Okay, and then we use chi-square tests for population testing, for population variance, for goodness of fit, and for testing independence of tests for independence. And F test we usually use to assess equality of population variances, for in ANOVA and COVA, significance of regression, joint hypothesis in a multiple regression setup. So in all those cases we have seen that we are using an F test. Okay, then we learned something about relationship between qualitative variables. So this we could get from the contingency tables. We learned about how to get odds, how to get odds ratio. We also learned about how to get conditional probability from this contingency table, how to get odds ratio, how to obtain confidence interval for odds ratio. This is quite important. Okay, and degrees from when we are testing for independence, then we would go for a chi-square test based on the expected probabilities and the observed frequencies. So that thing also we learned. And if we want to find out the relationship between quantitative variables, we would look at the covariances or the correlation. The most popular one is the Pearson's correlation coefficient, where Rxy is summation in a two variable, so it will always be two variable only, by xi minus x bar whole square, summation yi minus y bar whole square, this thing. Okay, sxy by sy. This would be the Pearson's correlation coefficient. We also learned how to visualize relationship from a scatter plot. So we plot x and y, and then graphically we can see or assess what relationship probably two variables have. Then we learned about the least square principle, fitting OLS. How do we fit it? So we want to fit a line in such a way such that these vertical distances between the observed and the predicted, these vertical distances are minimized. So we want minimum means sum of squares of errors. So in order to minimize that, if you remember how we do it, we partially differentiate in terms of the unknown parameters of the model, equate them to 0, and solve the system of equations to get the beta hat values. Okay, and then also we learnt about coefficient of determination. So each of the total sum of squares is partitioned into sum of squares due to regression plus sum of squares due to errors. So r square would be sum of squares due to regression by sum of squares due to errors. So we everything we learnt in terms of when we have one regressor, and also when we have more than one regressor. So it is worthwhile to remember one. So if I have this as my general model, where x is like 1 1 1 1 1, this is the model matrix, and here I have x1 x2 x3, something like this, x1 1 x2 1 x3 1, x2 2 x2 2 x2 3, and so on x2n, something like this. Then beta hat would be x prime x inverse x prime y. So here this is, let's say, x1, this is x2, our model, if we write it, it would be beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. This is my model. So if we solve for this one, we would get a 3 variable vector where this would be beta 1 hat, beta 2 1 hat and beta 2 hat. Okay. So this is the thing that we can obtain directly from the software and indirectly by solving, manually by solving these matrix equations. Okay. And in week 5 we discussed the types of ANOVA. It could be a one way or an n way ANOVA. So what is meant by an analysis of variance? So we would have factors where each factor would have level 1, level 2, let's say level L. So let's say this is something related to eye color, and eye color could be of 4 types, and let's say this is influencing on some variable y. Okay, so then these 4 categories, let's say blue, green, brown, black, these are the levels. So let's say this is level 1, this is level 2, this is level 3 and this is level 4, but this eye color is the factor that we are considering in our model. So while doing this, if we have to fit this on this would be a one way ANOVA model. Essentially what is being ANOVA can be also looked as a regression with dummy variables. Okay, so that thing also I think we discussed. So we learned about factors, levels, we learned about the ANOVA identity as I was saying. So SST would be SS due to this treatment plus SS due to errors. Okay, or SS due to factors. So this partitioning of total sum of squares is something that we learnt about, and the ANOVA tables, we knew how to obtain the ANOVA tables, get the F test, and also we learnt about two-way ANOVA where we have two factors instead of one factor. So let's say if I say eye color and eye shape, so these are like two factors which are influencing on y star, and we would have main effects something like this and also interaction effects something like this if we include an interaction term in our model, and we can test for each of these using an F table. Okay, and as I was saying, there is so much similarity between regression because ANOVA would mean regression with dummy variables. Okay, in week 6 we learnt about index numbers and time series. So we learnt about simple and complex indices. We could have simple aggregative indices or simple average of relative indices. Relative indices would be this P1 naught by P naught I, P1 I by P naught I, and then we would take a summary of these things. Okay, these would be the relative indices, and then we would take an average. We also learned about weighted aggregative indices like Laspeyres index and Paget's index, where Laspeyres is weighted by price. Weighted by price or quantity at base period, and Paget's is weighted by price or quantity at current period, and Fisher's is nothing but this is also we learned. This is like the ideal index that we should use for price or quantity. Okay, and we also learnt about the cost of living index, and as I was saying, we learnt about time series, trend, seasonality, cyclical, and we learnt about decomposition of time series, how we can model, we can fit trend lines or we can get moving averages, and then we could add those trends, estimated trends or estimated seasonality in in our regression model. We can add seasonality as a categorical variable, and then we can find out the relationship between uh, 1x and the time series that we are trying to find out. Okay, and also we learned about some forecasting and smoothing methods. So one important one is the exponential smoothing method, and this is a method of forecasting. For all practical purposes, we should not use exponential smoothing to forecast very future values. It should be restricted to near future. Okay, same for moving average, this is also a smoothing technique, and also we learnt about how to check for accuracy. So after that, during week 7 we learnt about the classical linear regression model and the Gauss-Markov assumptions. So the Gauss-Markov assumptions were that the homoscedasticity assumption, no heteroscedasticity, no autocorrelation. Exactly, we did not talk about autocorrelation. So what was the thing? We had this homoscedasticity assumption, we would have x as non-stochastic, and so on and so forth. There were 4-5 assumptions, so you should look carefully into Gauss-Markov assumptions. One thing we should note, that OLS estimation does not require normality assumption. This is only needed for testing. This is one point that we should be remembering. Is it okay? Yeah, so the Gauss-Markov assumptions were expectation of the errors or epsilons would be 0, variance of x should be sigma square I, variance of epsilon. It should have constant variance, like I was saying, homoscedastic, x should be non-stochastic. The number of observations should be greater than the number of parameters. Okay, so these would fall under Gauss-Markov assumptions, and Gauss-Markov theorem states if assumptions hold, then OLS are the best linear unbiased estimator if the Gauss-Markov assumptions hold. Okay, then we learned about how to get OLS estimation. The logic, as I was saying, if we have a plot over here, we want to fit a line in such a way such that these vertical distances are minimized, and the way to do is to write down the model, differentiate partially in terms of the unknown parameters, equate them to 0, solve the system of equations and get the values. Okay, so it's the same thing in case of one regressor or multiple regressor. I just gave you the formula for multiple regress when you have more than one regressors in the model. If you have one regressor, you can use the closed form, or all of these are closed forms for that matter, but you can use those beta hat estimates like xi minus x bar, yi minus y bar. Let's say this is the slope coefficient for a simple linear. I'll not write it here. Okay, somehow my pen is not working, just give me a minute. 1 second. All right. So then, how would we get an estimator of error variance? It would be the mean squared error. So if we get an ANOVA table, we get the sum of squares due to error divided by the degrees of freedom, and that would give us an estimate of the error variance. This is an important thing that we should keep in mind. And then we were talking about residual analysis, if you remember the previous day. So I was telling that if you have a simple linear regression, you can fit the residuals versus the x's, and it should have a non-random it should have a random pattern. It should be random with no pattern, or equivalently, and it should be clustered to near the 0th point, because we had this assumption that expectation of x lies is equal to 0. It should be clustered near the x residual equal to 0 line, y equal to 0 line, and there should not be any pattern. This one is equivalent to fitting the residual versus predicted. We would notice the same pattern, but in case of a multiple linear regression, then we should plot the residual versus predicted only, and there should be randomness in the residual plot. So these are all residual plots. Okay, and also if you remember, the residuals are also used for outlier detection. So we talked about this briefly. We talked about something called as standardized residuals, if you remember. So the way to obtain standardized residuals in our software, let's say we write something model equal to lm y on x data equal to data, and then just resid model would give us the only the normal residuals. But if I write our standard model, then I'm going to get the standardized residuals. Is it okay? Alright, I'll show you this thing when I go to the R session. Alright, so in week 8 we conducted tests of hypothesis like the t test or f test for joint hypothesis. T test, suppose if we have a model like this, then testing h naught beta 1 equal to 0, this is the t test that we can also obtain from our summary model command, if you remember. Yesterday I also showed how we can get the restricted regression, unrestricted regression framework. So if we have something like beta 1 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon, if we want to test for beta 2 equal to beta 3 equal to 0, this thing also we can use either t, because if we have beta 2 minus equal to beta 3, this can also be written as beta 2 minus beta 3 equal to 0. This we can either do it by a t test, or we can also use an f test. An important thing, an important identity is that t square equal to f. So t square n equal to f1n. Okay, this is an important relationship between the t random variable and an f random variable. Okay, and then we also talked about the omitted variable bias and how it can be tackled using an instrumental variable regression. And then we also talked about the testing for appropriate choice of functional form, which is the Ramsey's reset test, which assumes that the h naught is expectation of y given x is a linear function of x. So I'm going to show you how you can do this Ramsey's test and White's test for heteroscedasticity in a little while. So White's test is also that testing for heteroscedasticity, and Ramsey's reset test is to test whether the linear functional form choice is the correct one or not. So I'll just stop my screen here for a brief moment, and please let me know if you can see the R screen.
Visible, ma'am.
Visible, right? Okay, so I'm going to remove everything from here. Okay, so sorry. So first things first, I'm going to set the working directory. Okay, so data, I'll write it as my data equal to read.csv whitetest.csv. So here I have data on 3 variables where I have income in lakhs per annum, years of education, and year of job experience. Okay, so now in order to do Ramsey's reset test or anything, we have to carry out a regression analysis. So for regression, it's a what we have to do. Let's say I write model equal to lm. Y is my income.lpa, so I am going to write income.lpa. Please keep in mind we have to use the exact command column name. Okay, so this will be years dot of dot education plus years, this years I have written small, so I'll have to write it in lowercase, years of experience, where my data equal to my data. There's some problem they are saying. Okay, so LPA 1.
Year of jobs.
Years of job. And also I have to put an LPA dot over here, it seems. Okay, So now my model is ready. I can get a summary of the model to find out the coefficients. So see, here I have the T statistic, and both years of education and years of job experience are highly significant. I have a high multiple R square value, and the regression also overall is significant because this p value is very low, the F statistic value is very high. Okay, so now I want to test if okay, so before even going into that, I'll show you how this this resid thing that I was talking about. Okay, so resid model will give you the residuals, but if you do R standard, then these are the standardized residuals. You can see this regression diagnostics. Okay, R student would give you the studentized residuals. DF we talked about, if you remember, some DF fits. So you can also obtain the DF fits using this thing. DF betas, Cook's distance, these are some of the metrics for testing the regression diagnostics. Okay, so all of these you are going to get it here. So you can use these commands in order to test for outliers and in order to test for influential observations, and these are all included in the base stats package, so you need not have to import or get any other specific package in order to use this test. Okay, now coming to Ramsey's reset test. So this is a test for, as I was saying, model specification, where my H naught is the regression line that we have, expectation of y given x is a linear function of x. This is what we want to test. So in order to use this test, we need to get this library. Okay, without this library LM test, we are not going to have this. So then once this library is loaded into memory, we have to use reset test. So you see, if you press F1 over here, we have this reset test in LM test package. It will perform Ramsey's reset test for functional performance. Okay, here are some other parameters you can use. We'll use the default one. So if we give reset test model, what do we get? So we get this as my output. This is the reset test statistic. These are the these are the degrees of freedom that we want of the F test, and this is my p value. So judging by p value, what do we find here? We see that p is greater than 0.05, hence we do not reject H naught and conclude that there is no misspecification and the relationship is linear. We don't know if it is actually linear or not. There's no evidence, there's not sufficient evidence to reject the hypothesis that this is linear. Okay, so these two are very important, LM test and reset test. Okay, all right. So once we are done with it, now we want to test for heteroscedasticity. So before that, we can, as I was saying, if there is heteroscedasticity in the model, we might have some we can get an idea of something is wrong by looking at the residual plot. So if I just, as I was saying, if I get a plot of the residuals, resid model, and this would be my x, so this will be y, we would plot residuals on y, and x equal to, we would have the predicted. So as I was saying, for multiple regression we would plot residual versus predicted. So this will be y x equal to predict model, y equal to resid model. So let us see. Oh, I missed a bracket here. If I add a line, add line h equal to 0, so you see this is scattered randomly about 0. There doesn't seem to be any such pattern. So it is probable that there is no heteroscedasticity in the model. But we should go ahead and test it. So if I have to use the White's test, I need to import this library. Okay. And then I should use White underscore test. This will perform a White's test for heteroscedasticity, which determines whether the variance of residuals in a regression model are constant or not. Okay, here the test is also given. This is the test statistics as we talked about, n r square, where r square is like this equation, where we are obtaining the residuals from the first fitted model and then uh, fitting it. So these equations you will find in the class notes and those kind of things. Same thing, it is being performed over here. So if we write this thing White test model, the observe or outcome will be something like this. The null hypothesis is homoscedasticity of residuals. Alternate hypothesis is heteroscedasticity of residuals. Test statistic is 0.2, p-value is 0.9, which is quite high. So we do not reject the null hypothesis and conclude that there is no heteroscedasticity. It is homoscedasticity as reflected from this plot. Is it okay?
Okay.
Okay. All right. I hope I'm back in the PPT. Now this one, we were talking about autocorrelation and multicollinearity, how to detect and what associated we should know, what could be the associated problems. We would have inaccurate estimates with larger standard errors and wider confidence intervals. That is not desirable. So as I was saying, any stochastic process can be either stationary or non-stationary. So time series is one such stochastic process. As I was telling, ARMA model, how we should determine the ARMA PQ models, Q from the ACF and P from PACF. So for AR1 model, we what we deduced what should be the stationarity condition. We should have rho less than 1. We also talked about positive and negative autocorrelation, and the important thing is to please keep in mind this line where of the Durbin-Watson statistic, 0 towards 0 is positive, towards 4 it's negative, and also there were some intermediate Durbin-Watson points which were given. Okay, and based on that, these regions would be where we would these would not be conclusive. Other than that, beyond this point it would be negative, beyond this point it is positive, and beyond within this region we would have that it is no autocorrelation. Okay, so please keep this line in your mind, Durbin-Watson statistic. And then we saw how to get the statistic from R also. And then as a part of remedy, we learnt about the generalized least squares. We also learnt about multicollinearity detection. So how do we detect for multicollinearity? We can check for pairwise uh, pairwise R square to see if the two regressors that we are considering, they are highly correlated with one another. Okay, and also we learnt about something known as VIF. Okay, so this is the variance inflation factor, which is nothing but regressing. So VIF is, if I have to find out VIF associated with x1, so I'll write it here. Suppose I want to find, I have x1, x2, x3 in the model. So if I have to find out VIF associated with x1, I am going to regress x1 on x2 and x3, get the R square from this model, R square x1 from this model, and then VIF x1 would be 1 by 1 minus R square x1. And then if this is greater than 5, we would suspect multicollinearity. If it is greater than 10, we would say that there is multicollinearity. Okay, this also we talked about. And so yeah, as we were saying, stationarity conditions. So stationarity means expectation if xt is a time series, then condition of I should call it as weak stationarity is expectation tt equals to constant, does not depend on t, and variance of xt is also constant, and correlation between epsilon t and or xt minus l is only a function of the lag and nothing else. Okay, so we talked about differencing in order to remove the trend components, or in order to get to from a in order to go from a non-stationary time series to a stationary time series. And if we have trends in the model and seasonality, so deseasonalizing the trend will remove these parts and make a non-stationary, can possibly make a non-stationary series a stationary one. Okay, and then we talked about the modeling part, where we could have autoregressive processes, moving average processes, we could have a combination of both, and we could also have autoregressive integrated moving average, where D would refer to dth order of differencing. Okay, and we also learned a little bit about co-integration, how we can use two series to to predict how in future they are going to affect each other. And very briefly we learned about error correction models. So from this time series part, these modeling parts, trending, detrending, deseasonalizing, those are really important concepts. And how we should get these orders from the ACF PACF graph, what do they signify, if we have an AR1 process, then the Durbin-Watson statistic, these are of importance and we should know this. Okay, and then for week 10 we learnt about regression with dummy variables, where we could have an independent variable as a dummy, or we could also even have a dependent variable as a dummy. So then this would no longer remain a linear regression. We would either have a logistic or probit regression where we have a simple case where the dependent variable is binary, either yes, no, male, female, can be coded as 0, 1. In such cases, we can have the logistic or the probit regression. And we also saw what would be the associated problems with linear probability model. So our y values would be here, but the regression line would go well beyond, and then truncation would again create some problems. Okay, I hope you remember these. So did I cover everything, whatever we were talking about? Oh, okay, no. Yeah, so I'm sorry for this back and forth thing, but we were in multicollinearity detection and then we went somewhere else. Okay, also we learned about this structural breakpoint thing that we learned from Chow test. So what I'm going to show an illustration of this test using R as well, so that you know how and when we can use it. So again I'm going to stop the screen. Okay, so let's suppose I'm going to clear this. Alright, so let's suppose I have a data frame like this. This is my data frame. I have a value x and y. Sorry. Okay, now if I plot this thing, here I'm using a fancy way of plotting. This package is very important, ggplot2, and you can customize and create very nice looking beautiful plots. So here I'm using that. Let's say I load this package and I create a scatter plot. So I have to supply the data frame name, and then as AES I have to give the x values, whatever I want as x, the y values that I want as y, and we want a scatter plot. That's why I have to, since I want a scatter plot, I have to introduce this geom point and specify this color and the size of the points here. Okay, so if we run this, I'm going to get a line like this. So if you look very closely at x equal to 10, there seems to be a structural breakpoint. It apparently looks like that till x equal to 10 the line was this, and then this has not continued in the same trajectory. It has gone like this. Both the slopes and intercepts seem to have been changed. Okay, so point 10 could be a potential structural breakpoint. So in order to test whether this is the two regression coefficients, both the intercepts and the slopes, whether they are same or not before 10 and after 10, we would have to perform this Chow test. Okay, now what we are going to do is that first of all we are going to load this library struct change, because this contains that Chow test. So if I load it, this is already loaded, and then I perform this thing. So I have to use this command sc test where I'm going to plot this data. First I have to supply the formula to this command. So the formula is I'm regressing y on x, and the type of test that I'm going to do, structural change test, is chow, and the point about which we should differentiate the two regression equations that I'm going to fit is 10. So I'll see if what is the value. So see, the chow test f value is highly significant because p value is very very low. So the null hypothesis was, so if I can close this screen 1 second, so I'll move back to the PPT now. Okay, so this was the structural breakpoint test. So if I have a chow test, let's say this was point 10 and this was beyond 10, so this could be a structural breakpoint that we want to test. Okay, so here I have one line beta naught plus beta 1 x, and here I have another line beta 2 plus beta 3 x. So my h naught is beta naught equal to beta 2, beta 1 equal to beta 3. And from the R software we see that the f value is something approximately 110 and p value is of order 10 to the power minus 13, which is very less than 0.05. So what do? We reject h naught. So here what do? We reject h naught and conclude that 10 is a structural breakpoint. Is it okay?
Okay.
Okay. All right. So again we coming back to the discussions. So we learned something about the dynamic modeling also. We also learned about Granger causality, where one series we say is Granger causal for the other series. So very briefly we learned about Granger causality and also about spurious regression. Then we moved on to the concepts of stationarity, as I discussed a while back, and finally we went towards conducting regression with dummy variables. So as I was saying, we could take independent variable as a dummy and we could also incorporate dependent variables as a dummy, and that would be logistic and the probit regression. And we should know what are the problems that are associated with this linear probability model, what are the error assumptions on distribution of errors. So for a logistic regression we assume that the errors follow a logistic distribution, and for probit we assume that the errors follow a normal distribution. Okay, so now I'm going to show you with the software how we can incorporate this dummy thing and carry out regression with dummy variables, or popularly you can call them as ANCOVA, because it's essentially the same thing, but still I'm going to show you that. All right. Okay. So let's say I'm going to incorporate another variable here. 30 observations I have, no? So uh, thirty observations, let's say. So if I do so I have a 0101 variable. I'll look at the data here. So I have 01010101, something like this. So this is my dummy variable. Let's say I want to regress. So here I am going to regress y on x and z. Okay. So what I am going to do is that I have to write data $z equal to as dot factor. So if I do a structure data, so you'll see x is a numeric column, y is a numeric column, but z is a factor with 2 levels. So now this variable has been made into a categorical variable. So now when I do lm on data $y on data $x plus data $z, then I have the coefficients. If I have to do this dummy reg model, this, if I store it like this, then summary is this thing. Okay, so this one I know it has incorporated this as a factor variable. Okay, if I want to look at this, if I want to look at the model matrix, then I have to write model.matrix dummy reg model. So okay, these were 2 levels, so they have just included one variable in the model. I don't think this is as clear as I would want it to be. So let me just introduce another gender column. Okay, so data let's say gender equal to, I'm going to write 30 male female things. Five, okay. So now I'm going to change a little. Okay, so I have this. So now my data set has x, y, z and gender. If I do a structure of the gender, I'll have this thing. Even though it will take, I'm going to enforce this thing. Data.gender equal to as dot factor. Okay, let me do one thing. Instead of this z variable, let me introduce something else. income, let's say, let me introduce low, medium, high. Okay, so this is low, medium, high. Medium, 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 low, medium, medium, high, 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 medium, 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 low, 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 high. Okay, so if we do this, then I'm going to see, yeah, if I do as factor, data dot income equal to as dot factor data dollar income, then we'll see this is a factor with 3 levels. Okay, so I should essentially have 2 dummies. I'm going to remove this thing entirely and I'll run it again afresh. Okay, so here we had the data frame, this was the plot, and we did the chow test and all. Now the data is x and y. I'm adding an income column. So now my data set has x, y and income. Okay, so dummy regression model would be this on this and this one income. So now you see I have 2 dummies. Can you see this thing? It's clear. So since I did that this on income, here the base, the highest income has been taken as base 0 0 dummy. The first dummy, this is one dummy accounting for low income, this is the second dummy accounting for middle income, and there is no dummy accounting for the third high income because we have an intercept term. If we had included that, we would have surely gotten that problem of multicollinearity. Okay, so if you have to incorporate dummies as regression into your regression model, the only thing to do is that to incorporate it as a factor here. Okay, now if I look at the model matrix, I'm going to show you. See, this is the model matrix that I have, the intercept turn, the x values that we have had, and this is the 1 0 would be low income, 0 1 would be medium income, and 0 0 would be high income. So can you see the similarity between ANCOVA? So here if I say that this income is a factor with 3 levels, and also I have a continuous covariate. So this regression, whatever I am doing, is essentially doing an ANCOVA model. Is it okay? Is it clear how we should incorporate dummies as a regressor? Okay. Fine. So now we have introduced dummies as regressors. What about dummies as response variables? So we knew that we can use, I'm going to remove this thing entirely. So now I'm going to show you how you can calculate or you can get logistic regression equation from by using R. Before that, I'm going to load a data set called empty cars. Okay, so this is a data set which has information on 32 car types and their associated variables. So if you want to, there are inbuilt data sets in R which you can go and explore. In order to do that, you can go to these packages or help section and just type empty cars. So this R documentation is going to arrive. This was extracted when and how It covers 10 aspects of automobile design and performance for 32 automobiles. Okay, so mpg is miles, cylinder is this number of cylinders that they use, this is a displacement, this is horsepower, the weight of the machine, then the engine shape, transmission, number of forward gears, number of carburetors. Now suppose I assume that the engine type is dependent on the weight and displacement. Okay, so then I want to assume that this thing Vs depends on weight and displacement. So if you go and see here, weight is a binary category. Okay, or even if I want to look at transmission, okay, 0 for automatic, 1 for manual. For the timing, let me look at this thing only. So here you see this is a categorical variable, or very specifically this is a binary variable. Okay, so here I won't be able to fit a linear regression, but what I can do is I can fit a logistic regression. So in order to do that, what I have to do is that first I have to okay, so this is with data sets, this is fine. Okay. So then I can write it model logit equal to, I have to use a function which is known as GLM. Okay, so GLM, this one, this variable, that write the formula on weight plus displacement. So before going into everything else, let me look at this GLM function. So this is going to fit a generalized linear model. So in family we have to specify what should be the family that we are using. Okay, here we have a description of all the families. So we could use a binomial, a Gaussian would fit a normal linear regression, we could fit a gamma regression, inverse Gaussian, Poisson, quasi binomial, and so many things. Okay, so here I want to fit a logistic regression, so I'm going to use this thing. So I'm going to write family equal to binomial, and within bracket I'm going to write, this is the default link, but even then I'm going to write the link function as logit. Okay, and the most important thing that I keep forgetting, I have to mention which data set it should consider. Okay, so now, so if I look at this, then this is my logistic regression that I have here. Okay, so if I have to write it down in terms of uh, the interpret, in order to interpret, how will I write it? So 1 second. So here I have, okay, so this was log by 1 minus p by 1 minus p equal to alpha naught plus beta naught weight, sorry, beta 1 weight plus beta 2 displacement. Let's say where p equal to probability that Vs equal to 1. This was my entire model. So alpha naught hat I have obtained as from this thing. Okay, let's say this is my model. So here I have So this is my alpha naught hat, this is beta 1 hat, this is beta 2 hat. Now how will I interpret this one and this one? So if you remember, we had to do some exponential transformation in order to, so what it essentially means is that 1 unit increase in beta in weight increases logit P by 1.62 units. So what it essentially means is that, I'll rewrite, increase in weight increases logit P by 1.62 units. So it means that P by 1 minus P increases by e to the power this 1.62 units. So what is e to the power 1.62? This is equal to 5, approximately 5. So if I can move it this way, so P will be 5 times 1 minus P. So 5 by 1 minus P is the odds of so what it means is that the odds of getting V equal to 1 is 5 times the odds of or odds of getting V equal to 1 increases by 500%. Okay, this is how we should interpret. Is it okay? Whatever coefficient value we have,
Ma'am, 1.62 is the coefficient hour, and 5 is our odds.
And 5 is the odds of increasing.
Odds ratio.
Yes, 5 is the odds ratio.
Odds ratio. Thank you.
All right. So this is how we would interpret the results. Now if you want to have a probit model, one second, I'm sorry. So if you want to have a probit model, we just have to change this link. GLM VS. Oh, okay, you're not able to see my screen, I think. One second. Okay, so if we want a probit model, we would do weight plus displacement, data equal to my data, family equal to binomial, link equal to probit, and then you would get the probit model. Okay, so now if you have count data, these were not discussed. If you have count data and you want to fit a Peugeot generalized least square with this Poisson family, so we have to use this log link Poisson. So there are several other things which you can use and get the um, estimated regression equation and the generalized least square models. Not generalized least square, generalized linear models. Okay, so that brings me to another point. So sorry. Okay, so there are difference between generalized least square model, sorry, GLS, and generalized linear model, GLM. Okay, so this one we would use in places of where we would have, you know, autocorrelation or heteroscedasticity, where we get the generalized least square by fitting. So the OLS estimate in this case, if we have, so let's say this V is my variance covariance matrix, then X transpose V inverse X inverse X transpose V inverse Y, this will be the GLS estimate. Okay, but generalized linear model is different. It differs when the response can be count, can be binary, or it can also be linear. So all of these fall in this generalized linear model class of category. Okay, so this one and this one are essentially different, GLS and GLM. So please keep this in mind when you do something else. Okay, these are not same concepts. All right, and then in week 11 we learnt about simultaneous equations modeling. We also learnt about endogenous and exogenous variables. So the difference is that exogenous variables are in turn not affected, but endogenous variable, they are going to affect and in turn they are going to affect and get affected in also in the system, like demand, supply, and this could be some temperature or other external factors. Okay, and then this is also very important, the necessary and sufficient conditions for identifiability. So if you remember, there was this rank order thing which would tell me in a simultaneous equation modeling system how we can say which equation is identifiable. And then we learned about the estimation methods like 2SLS and those kind of things. Very briefly this was discussed, and then we learned something about the panel data regression models. We could use dummy variables or we could go for some fixed effects modeling. So, and then week 12 was based on the R sessions, where we were shown how to use a few of the, like this was a hands-on thing. Okay, we learned a few commands and how to go about. First things first is to plot, and then so if I have so in order to summarize whatever we have done so far, if we have a data set at hand, So as a final summary, what I can say is that if I have a data set at hand, the first thing is to explore the data set by types of variables, and then types of variables what, and then get the charts or uh, distribution diagrams. If we have some theory in mind or question, so we fit those models, judge goodness of fit, then test for significance of the coefficients, and if all of these are significant, then we go for some sort of residual analysis, and then after doing everything we make the required conclusions. Okay, same for a regression setup also, and for a time series setup also. The first and foremost thing is to look at the distributions and be it a scatter plot, be it a frequency distribution, be it anything else. Okay, so the first and foremost thing is, while you get the data set, you just look at what sort of variables we have, what are the data structure, whether it is continuous, whether it is categorical, what models we can fit, and then proceed accordingly with the existing set of tools. And also, if there are any assumptions in mind after fitting the models and all, we can also go for testing of those assumptions. And one more thing is that if we have some outlier, we should detect and remove outlier, influential observation, so those kind of things. So even though this can be related in the regression concept, even in case of time series also, we should first go for plotting, then try to find out the different components, try to remove the non-stationary part, get the stationary distribution, and then try modeling on that. So that was all about this course. Any questions on today's session, or in general, you can ask me.
Excuse me.
Yes.
Ma'am, what is the log likelihood?
Okay, so suppose you have a random sample, let's say from let's say binomial distribution. Okay, so then the probability that x1 x2 equal to the joint this thing is it's a random sample, I've said. So x1 doesn't depend on x2. So this one I can write as product of y equal to n, xi equal to xi, something like this. So product of I equal to 1 to n, I write the PMF, NCX or NCI, p to the power I, 1 minus p to the power n minus I. So this thing is my likelihood. Okay, now if I take a log of this thing, then this thing becomes the log likelihood. Okay, so the joint PDF whatever is we have, that will only joint PDF or joint PMF, that is essentially the likelihood. Okay, and if we take a log of that thing, then that would be log likelihood. this is, I'm talking in terms of
Okay, ma'am.
I'm talking mathematically. Likelihood is that given what is the probability that your parameters are theta given you have an observation x. This thing is called as likelihood. And PDF is like what is the probability or density of x given the unknown parameter. Okay, so but even though this is like so this term would also involve x and thetas, this term would also involve x and thetas, so mathematically these two are the same thing. If you have to solve anything, then just write down the joint PDF of your random sample, that's the likelihood, and take a log of it. Conceptually it is that the probability that your unknown parameter is so here in this case your unknown parameter is p, so likelihood of p given you have your data as x. Is it okay?
Okay, ma'am. Ma'am, when we run a logistic regression analysis, the most of the cases we get the value of this log likelihood is in negative.
When we run the logistic regression, so we get the, I mean, these intercepts or coefficients, they can be positive or negative. There's no bound to them being positive or, I mean, or negative or positive. Or the, you're talking about the intercepts, right? Sorry.
Clear.
Okay, so so that so that we do not put any bound on the estimated coefficients, that is the reason we, you remember I told that we use this sigmoid graph, so that the right hand side can take values from minus infinity to plus infinity, and using that log transformation on p by 1 minus p, we are transforming the left hand side also from minus infinity to plus infinity, so that there is no problem. There is no bound on the
And
coefficients of a logistic regression. And
ma'am, can you define the ROC curve? Yeah, ROC analysis.
ROC, if I remember correctly, is sensitivity by 1 minus specificity. Is it, if I am not mistaken? And this is sensitivity. So if I have let's say this is my actual versus observed, yes, no, this is also yes, no. So sensitivity means what? One second, I'll just be extremely cautious and sure. Okay, so this is like true positive, this is true negative, this is actually no but observed yes, so this is false positive, this is false negative, falsely negative, observed negative but actually it is true. Okay, so sensitivity equals to true positive among all actually positive, if I am not wrong. One second. Yes, true positive among all positives. And specificity is one second. Sensitivity is this thing. Specificity is uh, I think 1 second. This is the true negative by all negatives. That is actually negative. False positive plus true negative. So 1 minus specificity would be false positive by false positive plus true negative. So we plot this, and the curve that we get, we call it as an ROC curve. So 1 second. So this is the true positive rate and this is the false positive rate. So we get this ROC curve, we get the area here. If this area is the higher the area under this curve is, the more accurate will be our results. So the thing is, if you have to correlate it with the logistic regression, so based on the uh, equation predicted values, you would have something like observed. Okay, and actually based you have, so essentially what we do, we split the data set into a trained part and a test part. We fit the model on this trained part. Okay, and then uh, based on we obtain the predicted equation, get the predicted classification for the test part, and we also have the actual observed value for the test part. Okay, we plot these true positive rate and false positive rate, and then we get the ROC curve. So the area under ROC curve, if it is like 0.8, 0.9, closer to the higher it is and closer it is to 1, we say that the model is able to classify well, that it is able to put negatives to negatives and put positives to positives in a proper way. So that is one criteria which we would want. We would want to increase this area under this ROC curve as much as possible so that we have more accurate results. Okay, so if we have a
Okay,
curve
thank you.
like this, then the area below this would be 0.5. Then we would say that the model is half time it's performing well, half the time it's not performing well. So then in that case we will not be very sure about the model. But if it is like this thing and the area is 0.8, 0.9, close, the higher it is to 1, we can say that our actual classification model is better that way. So in order to make it better, we can incorporate new variables, we can make transformations on the older variables, we can remove outliers and do all sorts of things. Okay, so this is the ROC curve where we plot sensitivity versus 1 minus specificity. Okay, anything else? And also
No,
one
thank you,
more
ma'am.
thing, we would want, so both the things, these are all error rates, right? The sensitivity is like true positive rate, and 1 minus specificity is like false positive rate. These terms are used interchangeably because this is false positive by this. So we would want, ideally we would want a curve to be like this. So that the sensitivity is also high, the true positive rate is high, and the specificity also is low. So this kind of classifier we would, I mean, this would be a better classifier. If I have something like this, which a line like this, then I would prefer that model. Is it okay?
Okay, ma'am.
Okay. Anything else? Okay, so if not anything else, then thank you so much for joining these sessions, and all the best for your exams if you have opted for one. And if you still
Thank you,
have
ma'am.
further questions, you can post it in discussion. We'll try to figure those out. Thank you so much for joining.
Yes, many thanks.
Thank you, thank you. So I'm closing the session now.
Thank you, ma'am.
Thank you.
Okay.